Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics. Now, we have been going through a series of lectures intended to the students of electronics in particular with regard to the paper 3 with the title Physics of Materials, and in this paper we have the section on bondings in solids. Now, we have been seeing the different kinds of bondings which exist in solids, namely ionic bonding, covalent bonding, metallic bonding, van der Waals bonding. Now, the first 3 are the primary bondings. Van der Waals bonding is said to be the secondary bonding or a weak bonding. Now, the contents of this lecture, that is lecture 6, are as follows. The title of the lecture is covalent solids and metallic bonding. The contents are binary and ternary semiconductors. So far, we have been seeing about silicon or germanium, but now we will pass on to gallium arsenide and other ternary semiconductors, and the notion of mixed bonding, properties which could be evaluated from the bondings, namely the covalent ionic bondings, and then lastly the metallic bonding, an introduction to metallic bonding. So, in the previous lectures I was talking about the hydrogen molecule problem. We started the hydrogen molecule problem, and what is the bonding in the hydrogen molecule? There are 2 hydrogen atoms which are coming close to each other, they are bonded, giving rise to the hydrogen molecule. The bonding in hydrogen molecule, as all of you know by now, is the covalent bonding, where the 2 electrons are said to be shared equally, but sharing is not a very good terminology. Sharing is not a good term to be used, because you do not have consider the electrons as particles. There is a charged cloud, because electrons are quantum mechanical objects. They are to be treated on the basis of Pauli principle, which we discussed in detail. Now, the hydrogen molecule problem was first discussed in detail by Heitler and London. So, the credit goes to Heitler and London, and this problem of hydrogen molecule is of great significance. Later, Heisenberg used the same kind of study for some other area which is not related to bonding. So, it carries lot of significance. I showed you a curve, the curve connecting the energy and the distance separating the 2 atoms. The lower curve, the cohesive energy curve, gives the formation of hydrogen molecule, whereas the other one shows something else, right. Now, we will see that in the time to come, but anyway the Heitler-London model of the hydrogen molecule, that is what we saw in the previous lecture. We also discussed about silicon, and silicon, what is the bonding in silicon, that all of you know, as you know, very many semiconducting devices are made up of silicon. Therefore, the bonding in silicon is covalent, and I would like to underline that the bonding is fully covalent, because all atoms are identical, right. The octet rule is obeyed, as I told you in the earlier lecture. They are fully covalently bonded solid. Now, the other systems which could be obtained from combining the third group elements like aluminum, gallium, this is the fourth group, right? Carbon, silicon, germanium. They are silicon, germanium are the semiconductors. Now, you got a third group and a fifth group, right? Gallium is here, arsenide is here, then you have the aluminum here, phosphorus is here, you can have aluminum phosphide or gallium arsenide. They are the 3,5 compound semiconductors, 3,5 semiconductors, right? Now, similarly, you can have zinc, that is a second group, this is the third group, second group you got zinc, then you got tellurium here. So, zinc telluride, right, and these things they form the the 2,6 semiconducting compound. Therefore, you can think of 3,5 or 2,6 the compounds, and now when you talk of 2,6 or 3,5 compounds where you got dissimilar elements, the bonding will not be fully covalent, and so it is possible for bonds to be partially covalent and partially ionic in nature. Again, this we will see in detail in the time to come. Now, I showed you the methane molecule, right, showing the periodic table is that you can have combination of elements in the periodic table in which there will be covalent bonding. The example, the octet rule is obeyed. The examples are, now let me start. You have the H2 molecule where the bonding is covalent, then methane the bonding is covalent, then the elemental semiconductor silicon and the germanium, the sharing of electrons is quite true. The octet rule is obeyed. I showed you the previous lecture. If you count the number of electrons when you combine two silicon atoms, the total number will be 8, and that means the sharing is perfectly obeyed, the octet rule is obeyed. But what about gallium arsenide? You got gallium has got only valency 3, arsenic has got valency 5, and so sharing is not a good term to be used. Now, therefore, I raise the question, what about compound semiconductors, right? Whether the octet rule is obeyed, or what is the comment about the sharing, the comment about the nature of the bonding. It is not a fully covalently bonded solid. And so, if somebody asks a question, what is the bonding in a compound semiconductor like gallium arsenide, you should not tell the bonding is covalent, right? It is wrong. So, if you have ternary systems like AgGas2, they are called the ternary chalcopyrides, which are used for solar cell applications, the bonding is not covalent, and so covalent come ionic, and so you should be knowing fully well that the bonding is not covalent in all cases, right. And so, you have the compound semiconductors like gallium arsenide, gallium has got a valency 3, arsenic has got a valency 5, right. And similarly, 2,6 I have the indium telluride, right, as I mentioned just now, valency is 2 for indium, tellurium has got a valency 6. How can the electrons be equally shared, right? I raise the question, how can the electrons be equally shared, because one has got 2, the other has got 6. Equal sharing, that sharing is not a good term when you are talking about electrons in terms of wave functions or charge density. The sharing is not a good term, and again the bonding is not as a result of which bonding is not covalent, right, because what is NaCl? NaCl ionic bonding. In NaCl got ionic bonding because the electronegativity values are very much different. Similarly, here when you are combining two dissimilar elements whose electronegativity values are different, the bonding will be partially ionic. NaCl is fully ionic, right, whereas here there will be partial ionicity there, but in some cases the percentage ionicity even in semiconductors, the percentage is very large. That is important point to be noted, right. Therefore, let me now pass on to the ternary semiconductors like AgGas2, Se2, Tu2, they are the chalcogen atoms, right. Similarly, you can have ternary pnictides, right. So, ternary pnictides, ternary chalcopyrides. Now, these things are used for solar cell applications, and in these systems the bonding is definitely not covalent bonding. Covalent bonding fully covalent bonding come plus the ionic bonding will be present. Now, let me now pass on to the properties of some of the covalent compounds. Now, the covalent, the property or covalent bonding is present in gases, liquids and solids, silicon, and in gas like hydrogen gas, hydrogen molecule has the covalent bonding, methane and many gases. And so, gases, liquids and solids, there are several systems in which covalent bonding is present. They have low melting and boiling points. Obviously, electrical conductivity will be poor, and many are soluble in non-polar liquids, but not in water. And the other properties are, you have they are hard, like diamond. Diamond is one of the hardest material where the bonding is covalent. On the other hand, bismuth has got a weak bonding, right. So, when the bonding is very high, the covalent bonding is strong bonding. Diamond has got the the bonding is very strong. So, when the bonding is very strong, what about the melting point? What is meant by bonding? That is, the interatomic bonding is very strong. That means, the temperature required to break the bond should be high. When the bond strength is high, the bond length will be short, right, and the melting point will be high, because the energy required or energy to be given to break the bond will be high if the bond strength is high. So, the bond strength and the melting point are correlated with each other, and so your tungsten, and above tungsten you have got diamond, right. Diamond is the hottest material that you know. So, which has got a melting point of 3550 degrees centigrade, whereas bismuth has got a very low melting point of the order of this 270 degree centigrade. And again, in the case of semiconductors, the bonding is directional bonding. That of course, I showed you in the earlier lecture how electrons are occupying positions between the two germanium atoms, right. Extraordinary charge is accumulated, right, in the direction between the two germanium atoms. Therefore, it is a directional bonding, right. And so, let us now compare the ionically bonded solid and the covalently bonded solid. Now, the crystalline solid are made up of ions, right. In the case of ionically bonded solid, they have high melting and boiling points, right. And secondly, they conduct electricity when melted. How does the conduction take place? It is whether through the electrons? No, it is because Na and Cl are ions, you do not have electrons there. So, ionic conductivity, they are ionic conductors, you talk of fast ionic conductors. Now, therefore, the conductivity is due to the movement of ions. Many systems are soluble in water, but not in polar liquids. Now, we will pass on to metallic bonding. Now, you know it is a metal, right. Metallic bonding, what do you know about metal? Now, you have iron, copper, they are all metals. The bonding in these things are it is made up of course, that is a metallic bonding. And so, before going further, we will have a break at this point and then we will resume later. Welcome back to the break. So far, we have been talking about the two bondings, the primary bondings, namely ionic bonding and covalent bonding. In ionic bonding, you have got ions, positive and negative ions, right. And I told you some time back, the conductivity occurs in ionically bonded solids. So, the conductivity is due to the movement of ions, right, because you do not have electrons, right, you do not have. So, you have got only a collection of ions. So, when you heat it, there will be conductivity. If at all there is conduction, the conduction is due to ions. Whereas, in the case of semiconductors, the conductivity is electric conductivity is poor, but you can dope it, as I told you in the first lecture, you can dope it and you can make them to become good, I mean you can control the conductivity, right. The most important thing is you talk of p type materials, n type materials, and you combine these two, the electrical current can be controlled in the case of semiconducting materials. Okay. Then now we pass on to the metallic bonding. Now suppose somebody asks, in metals what kind of bonding is there, right. In metals, naturally the bonding that you have in metals is nothing but metallic bonding. So what are examples of metallic bonding? What are examples? All metals are examples of metallic bonding, right. All metals. Now you can take gold, or you can take aluminum, or copper wire is there. So all metals, they are stable because of metallic bonding, right. So how do you explain metallic bonding? Now sodium is a metal, right. Am I right? Sodium is a metal. Sodium is a liquid metal, right, because the melting point is low. Where do you use sodium? Liquid sodium, right. Liquid sodium is a coolant which is used in nuclear reactors and at certain other cases as well. Now let us look at sodium. Now sodium is a good metal, right. Now what is the atomic number of sodium? In the elementary class, the atomic number of sodium is 11. What is the electronic configuration? The electronic configuration will be 1s2, 2s2, 2p6, right, then 3s1. Now among 1s2, 2s2, 2p6, these electrons are called core electrons. They are called core electrons because their shells are completely occupied. You would have studied at a lower level, the electrons in any shell, if the shell is completely filled by the electrons, then the shell is of no use. The properties are decided not by the electrons in closed shells. Closed shells do not give rise to any current or any magnetic moment. It is only the electrons which are found in the outermost shell, the incomplete outermost shell. Now what is how many electrons you have got here in this case? You have got 1s2, 2s2, 2p6. P shell can have only 6 electrons, and all these shells are closed, right. 1s2, 2s2, 2p, all the shells are closed. They are called the core electrons. The electrons residing here, they are called core electrons. 3s1 is the valence electron, right. 3s1 is the valence electron. So the valence electron of atoms, or valence electrons of atoms, or valence electron of atoms, free electrons or conduction electrons in metals, right. Now this is a very profound sentence. What I have stated is of very great significance. The so called valence electrons of atoms become the free electrons or the conduction electrons. Why are they called conduction electrons? Because they are free. And so when the material is there, when you apply an electric field, if the material is there, if you apply an electric field, a potential, then the electrons will try to go in the positive, towards the positive electrode. So there will be a current, right. There will be current, the current will be opposite direction, electrons will flow in this direction, current will be opposite direction. Now therefore you have the concept of free electrons coming here, that is the valence electrons become the free electrons. Valence electrons of atoms become the free electrons, and once they are free, they do not belong to the parent atoms, right. They belong to the whole solid, and these free electrons are responsible for the electrical conductivity or thermal conductivity. You know about Weidmann-Franz law. The point is only the free electrons are responsible for electrical and thermal conductivities. Where from do you get free electrons? It is the valence electrons of atoms, they become the free electrons, right. That is very important. The valence, so it is very important. And where do you find these valence electrons? The valence electrons will be found anywhere, right. Here in atoms, you have the valence electron here, right. In sodium you have got a valence electron that will be revolving around the nucleus, right, in an atom. But in a, when you collect 100 sodium atoms, right, then what about the number of free electrons? Now, you have a metal here, you have got a solid here, right, solid piece. When the electron is stripped, what will happen to the atom? The atom will become positive ion. Earlier, each sodium atom had 11 protons and 11 electrons. It was neutral, right? Each sodium atom, every atom will be neutral. So, sodium atom has got 11 protons and 11 electrons. Now, when you combine 100 sodium atoms or 10 sodium atoms, what happens? When you combine the sodium atoms to get a solid, what happens is the valence electron gets freed, right. When the valence electron is lost by the atom, instead of 11 sodium atom will have only 10 electrons. There will be 11 protons and 10 electrons. So, it will become a positive ion. The sodium atom, which is neutral originally, it becomes a positive ion. So, that is what I am showing here. You have got a positive ion, the electron will be somewhere here, right. And similarly, this positive ion is here, the electron will be somewhere here. What I want to tell you is the electrons can flow very easily through the solid, something like a gas. You know, in a gas kept in a vessel, the molecules will be moving, right, here and there, right. They meet each other, collide and all. You have studied about mean free path, the collision probability and all these things in the earlier school level with regard to the movement of gas molecules. You talk of kinetic theory of gases, and similarly, like a gas, you call here a free electron gas. The electrons were treated like a gas, the classical gas that you know about, and so these free electrons move randomly, they collide and all, they go each other, I mean they move very freely, right. And okay, where from you are getting the free electrons? They are donated by the atoms, right. So, if you have got 100 sodium atoms, right, how many free electrons will be having? Now, according to free electron theory of metals, if you have got one sodium atom, it will give one electron. So, if you have got 100 sodium atoms, in principle there will be 100 free electrons which will be moving here and there. Okay. And so, this is again a primary bond, and in metals and alloys in general the bonding is metallic, it is one of the primary bonds. The point is the free electrons are responsible for the bonding, right. Now, the free electrons form like a glue. You got one, supposing you got only ions, that will be repulsion, right. So, the free electron present here, it removes the repulsion between the ions, right. It forms like a glue, something like a paste. The positive ions are embedded in a electron background. There is a charge background, electronic charge background in which the ions are sitting, right. That is how you visualize a metal, right. A metal is composed of ions and free electrons, right. That should be understood, and these free electrons are responsible for the electrical and thermal conductivity. Okay. And now, let us this is what I am showing, ions and electrons. How do you define a metal? You can write a metal is equal to ions plus electrons. The electrons are freely moving, right. You see the electrons here, they are moving, they are found somewhere here, you have the electron here, electron there and so on, right. They are freely moving, right. As time elapses, they will be found everywhere, and they may be hitting the ions and so on, right. So, okay. So, you have a sea of electrons, right. The metal atoms typically contain fewer electrons in their valence shell, and these electrons can be easily lost by the atoms and therefore become delocalized and form a sea of electrons surrounding a giant lattice of positive ions. Metallic bonds are best characterized by the phrase a sea of free electrons, and this sea is called the Fermi sea, because you know electrons have to obey the Pauli principle or the Fermi-Dirac statistics, and so it is called a Fermi sea, right, a sea of electrons, right, a sea of people in the beach, and similarly CF electrons in the among the metallic ions, right. Electrons in metallic bonding, valence electrons are not bound to the parent atoms, right. They drift through the entire metal. I told you about, so the electrons form a glue or a paste. These electrons have to obey the Fermi-Dirac distribution function. The flow of electrons give rise to electrical and thermal conductivities, okay. And the mechanical, magnetic, the important point that should be remembered is the mechanical properties, the magnetic properties, electrical properties, and superconducting properties, and very many properties of materials, they depend upon the free electrons, right. The core electrons are unimportant. I want to stress the core electrons are unimportant. They are only the valence electrons which become the conduction electrons or free electrons. They decide the electrical, thermal, optical, magnetic and superconducting properties. And so, in general the properties are decided by the free electron. That should be, that is a very important point to be remembered, right. So, what are the properties? By studying the covalent bonding or by studying the cohesive energy curve. I showed in the very first lecture the cohesive energy curve. In the earlier lecture also I showed the bonding energy curve. I showed two curves, the graph drawn between the energy in the y axis and distance along the x axis, the interatomic or intra-ionic separation along the x axis. You have got a curve like this, with going to the through the negative, it becomes a negative, and that is called the binding energy curve or the cohesive energy curve. And now, let me go through the properties which could be studied or determined from the cohesive energy curves of metallic materials. Now, the bond length can be determined, as I told you, and bond energy can be determined, the melting temperature, elastic bondless, thermal expansion, and again there is a correlation between melting point and bond energy. I told you the bond strength is very high, the bond length will be small, right, and the melting point will be high. Now, you know, in a gas the intermolecular distance is very large. When you have a liquid, the intermolecular distance becomes smaller. When you have a solid, solidification, condensation, the distance separating the atoms or molecules or ions will become much smaller. The inter-ionic separation will be of the order, how much will be the inter-ionic separation? It will be, you take all solids, right, you have in the universe, what is the distance separating the ions or atoms in solids, that you should know. Now, how will you determine the inter-ionic separation? Now, you make use of X-rays. You should know the X-ray wavelength region. If you know the X-ray wavelength region, then you can tell me the answer to the question that I am asking, namely, what is the magnitude which of the inter-ionic or inter-atomic separation in solid materials, right. Let me now pass on to summary part, and the summary goes as follows. Covalent bonding generally is said to be due to the sharing of electrons. That is not true. In the hydrogen molecule problem, it is okay. There are two electrons which can said to be equally shared. You have the Lewis structure. Lewis is one who showed how diagrammatically you can try to explain the bonding in many systems, but it is not true. Binary and ternary semiconductors comprising of atoms with different electronegativity values will have both covalent and ionic bonding, and valence electrons of atoms become the free or conduction electrons in solids. The very important message which I try to pass on to you, this should be borne in mind. This is a very important point in the summary, because it is the one that decides the properties. Valence electrons of atoms become the conduction electrons which decide the property. Now, let me pass on to the one more point is the physical properties such as the bond strength, melting point, bulk bondless, hardness, thermal expansion, all can be obtained from the cohesive energy curves. We will pass on to the question session. The question number 1, what kind of bonding is present in the 3,5 or 2,6 semiconducting compound, which is the hottest material you have in ionic solid, which is also having the highest melting point. From where do you get free electrons in metals? Where from you are getting free electrons in metals? And last question is, where do you find these free electrons in metals? What is the position which is occupied by the free electrons in metals? With this, we come to the end of the 6th lecture on bondings in solids. We will do the rest of the things in the time to come. Thank you.